Okay, welcome everybody. It's Monday, 5th of October, and you're tuned in to one of our regular fortnightly SUT lunchtime webinars. We have two speakers for you today on the subject of well plugging and abandonment. It's Yuejin Luo, and sorry if I've mispronounced your name. I'm sure you'll correct me as we go through, and Alasdair Brown. Alasdair has a BSc in Marine Geography from Cardiff, worked as a hydrographic surveyor, delivering and managing offshore geotechnical and geophysical survey campaigns for oil and gas and other projects, responsible for the application of unconventional survey methods and emerging technologies to reduce costs. His current role, he joined Charles Taylor Adjusting in 2018. Sorry, I'm still letting people in, so I get distracted occasionally. Handling the claims arising from damage to and loss of marine subsea equipment, such as ROVs, AUVs, and drill strings. Yuejin Luo has a doctorate in petroleum engineering. So is that from the Petroleum University of China?
No, in Edinburgh.
Oh, in Edinburgh. Okay. Yeah, excellent. Yeah, very, very good. No, it's just that one of our chairs of our Beijing branch is a professor at that,
okay.
which Frank Lim. So he has 33 years experience in drilling, completion and workover of oil and gas wells. He's worked for BP for 25 years, based in London, Aberdeen and Houston, and was the technical lead engineer for BP's global major projects and a project leader for well design standardization before joining Charles Taylor. Excuse me, just letting in a couple more. He's held well operation and engineering posts under a variety of operating environments worldwide, including land, offshore, deep water, salt drilling, etc. Managed numerous drilling technology development projects for BP and served as a well control specialist for a number of years, updating the BP well control manual for procedures in deep water ERD, slim hole and multilateral wells, developed well control software used by the drilling engineers in BP and other companies. He's a recognized technical expert in BP in well control, casing design, drill string design, drilling hydraulics, etc. Now, if I just let the last few in, I think we're ready to go. I believe, Alasdair, you're going to speak first. So I'll hand over to you, Alasdair. And as I said earlier, if anybody's got questions, please use the chat box, to put some questions in there, and we will have time, 15-20 minutes for Q&A at the end of the presentation. So first of all, over to you, Alasdair.
Thanks, Steve, and good afternoon, everyone. It's really great to see so many of you tuned in today. As Steve said, I'm Alasdair, and unfortunately today I'm without video capability, but rest assured you're not missing out on much. So before I hand over to Yuejin, we would just like to explain how this presentation was born. And it was actually an unplanned sequel to a wider strategic decommissioning presentation that we first put together in 2015. Many North Sea assets had and were quickly reaching the end of their design lives, and still are. And our prediction at the time was that for the next 10 years, from 2015, the industry would experience a huge amounts of decommissioning as operators followed in the footsteps of majors like Shell and Equinor, especially in the North Sea. Right, let's see if that works. Just flicking over to the next slide.
You want me to control, Alasdair?
Yes, please.
There you go.
Lovely. Okay. However, decommissioning activity didn't reach the levels expected, as illustrated by this slide, comparing the forecasted well decommissioning activity, that's in purple, versus the actual well decommissioning in yellow. Therefore, it would seem that age isn't the only factor, and decisions involved in decommissioning are far more long-term and complex than simply removing a platform and disposing of it. We also consider this as a challenge for the insurance industry, which is faced now with dealing with assets that are operating well past their intended design lives. However, today's agenda is purely technical in nature, as you'll see. Okay, next slide, please, Yuejin. Thanks. Okay, so plugging and abandonment is really interesting. Well, it's a really interesting standalone topic for two reasons. One, it's often overshadowed by the removal of topsides, which get all the press coverage. If you think about it, you always see images of the topsides being removed and various modules being towed into port for scrapping, but you never really see anything to do with plugging a well. Secondly, it might come as a surprise to hear that the P&A activity is the single largest cost element to decommissioning, accounting for about somewhere between 40 and 50% of the total decommissioning costs. On this slide, we can see that in central and North Sea regions, the expected cost of plugging and abandoning a well is about 3.3 million and significantly higher for subsea wells. So on that note, I will pass you into the capable hands of my colleague Yuejin to explain how one might go about P&Aing a well and various considerations before doing so.
Okay, thanks, Alasdair, and thanks, Steve, for the introduction. Right, okay. I'd like to start the discussion by first talking about the scope of decommissioning. Basically, the role the well P&A plays in the context of decommissioning. Then I'll talk about the purpose of the well P&A, the regulatory requirements in terms of permanent zone isolation, the well barriers, the well clearance, etc. Then I'll talk about the well status, various well status, and to show that it's important to understand the well status before we plan for a well's P&A. Then I use some examples to talk about the operational procedure for the well's P&A, and hopefully to show that you can see the well's operation procedures are very much well specific, depending on the well status, the well integrity issue, etc., etc. And also I'll talk about the time and cost for well and P&A before, and then I'll hand over back to Alasdair to talk about some future technologies to be used for wells P&A. Now, before the discussion, before they talk about specific for P&A, let's start to look back the history or the evolution of wells P&A in the oil and gas industry. Now, in the past, basically about 170 years. Now, in the beginning, in the oil industry, in the US, Pennsylvania, the wells were really very shallow. And the first well, I believe, drilled was only 69 foot. So basically about just over 20 meters deep. So when the well stopped production, the people just walk away from the well and basically leave the well as a gaping hole in the ground. And as you can imagine, the abandoned well would soon be flooded by groundwater, causing problems of production from other wells from the reservoir, from the same reservoir. So in around the turn of the century, regulations were introduced, which basically require people to plug the well to protect the reservoir, and not so much to protect the environment. It's basically protect their oil and gas resource. So it's only until about 1950s that requirements were introduced, which require people to use a specific material to seal the reservoir, basically using cement, bentonite, or clay, to seal the reservoir to prevent contamination of the fresh water, and not just as well as the reservoir. So, of course, currently the wells P&A is very much driven by environmental protection. But as a historical legacy, there are still lots of wells drilled before 1950s, which were not plugged or not plugged properly, and still cause problems in the environmental problems. Now, today in an offshore environment, well P&A basically as a part of decommissioning is really very much the beginning of the end for offshore oil platform and the oil field below. This picture shows the Ekofisk or offshore oil platform in the central Norwegian sector of North Sea. Now, as you can see, this picture, it's when we talk about decommissioning, it's very much people tend to think about removal of this giant steel structure, weigh of with over 10,000 tons. And it's quite easy to, to forget and to not see there are 3 wells below this platform. And before you can remove this giant steel structure, those 23 wells must be secured to prevent oil and gas leaks from those from the oil and gas reservoir, and which may have actually much bigger environmental risk than the platform itself. And in many sense, actually, to secure those 23 wells actually present much more challenges in terms of time and the cost, as well as environmental impact. Now, so when we talk about decommissioning, what it really means. Now, those are the statements I take from the BSEE website. BSEE is a regulatory agency of the US government. Now, from these statements, we can see decommissioning is very much include everything from, say, you shut down the production from the platform in preparation for decommissioning, all the way to, when the seabed and the ocean, basically the sea, returns to its original native condition. So decommissioning, in a general sense, really include everything starting from a plug, abandoning all wells supported by the platform. And also include you have to cut the well casings, conductors to below mud line and remove the production, the pipeline risers, etc., supported by the platform before you can remove the platform to its, from its foundation to below the mud line. And then, of course, you have to dispose the platform in an environmentally acceptable manner, etc., etc. So from this, actually, we can see wells P&A is very much an integral part of decommissioning. It's generally representing about 50% of the decommissioning cost. Now, I think it would be useful before we talk about specifics of well P&A, we have a quick overview of how we drill and complete oil and gas well. Now, in these slides on the right-hand side is a picture, at the top, we can imagine is a drilling rig on top of the offshore platform. Along the bottom is the oil reservoir, and in between could be, several thousand meters for formations, what we call the overburden formation. Now, to drill a well, the first step is always to install a pipe called a conductor. The conductor is very much a structural pipe to isolate the shallow, loose oil soil and also support the weights of casing, the wellhead, the BOP, blue water preventer stack, etc. And the conducting the North Sea, I always use North Sea as a general sense. I think probably most audience in UK. So in North Sea would be mostly, say, 30-inch conductor. Some subsea wells could be, 36-inch conductor. To a depth of, say, generally about 80, 100 meters, etc. So once the conductor installed, and then we'll drill the whole section, what we call the surface hole section, using a drill bait, which connected to the drilling rig by drill pipes, joint by joint. And we drill the surface hole section typically to 500-600 meters below seabed, and the size in North Sea could be, anything from a 7.5-inch hole to 24-inch hole could be, depending on the well design. Once the hole is drilled, and then we'll run a casing string called surface casing in this case, and the casing is run joint by joint, connected by using couplings. Surface casing can contain pressure. It's basically called a pressure seal. Once the casing, surface casing, once the casing installed, and then we will pumping cement around to basically fill the annular gap between the casing and the wellbore with the cement slurry. And then we'll install the BOP stack, basically called the blue water preventer stack for well control. Once this is installed, and then we'll drill the next hole section, which is typically in North Sea around the 12.25-inch hole, or could be as big as a 7.5-inch hole. So typically to say 1,000 meters deep. And then we'll run the next casing string, which could be an intermediate casing or production casing string. If it's called a production casing, basically what we mean is that the casing will be used as a secondary barrier when the well is on production. And similarly, we're pumping cement around to fill the gap between the casing and the wellbore with the cement. And then we'll drill the next hook section, which in this example penetrates through the reservoir, and typically would be 8.5-inch hole, 8.5-inch hole in diameter. And then we'll run a casing string again into the hole. In this example is a liner. So what we mean by calling a liner is that the top of the casing is not returning back to the drilling rig. Instead, the top of the casing only overlaps with the previous casing by, say, approximate 100 meters. And similarly, we're pumping cement around to cement the liner. And by end of this, basically that's the end of the drilling phase. The next phase will be called the completion phase. A completion phase would typically start by pumping seawater or brine, weighted brine into the well, clear fluid, basically completion fluid. And then we will run a tubing string into the well. And we are not cementing, we never cement the tubing string. Instead, we use a production packer, what we call the packer, to seal the annulus between the tubing and the production casing. Once the tubing string is run, and then we will run our perforating guns to punch holes through the production liner to establish the communications between the wellbore and the oil reservoir. And that basically will complete the drilling and the completion of the well. And of course, before we put the well on production, we have to install the wellhead at the top of the well. And then the oil will flow from the reservoir into the wellbore, and then through the tubing to surface, and then through the Christmas tree into the flow lines or oil and gas separators on the platform, etc. So hopefully the well will be on production for many years until it's no longer economical to continue. Then we'll have to think about plug abandoning this well. Now, when we plug abandon the well, we basically try to achieve 3 objectives. First of all, is basically to isolate all the formation fluids in all the permeable formations in the form of, could be hydrocarbon, oil and gas, or could be brine, a formation water brine, or could be gas, sulfur gas, etc., etc. Isolate those formations containing those fluids. And secondly, is to protect the freshwater aquifer for contamination. It's very much for land wells onshore. And thirdly, is to prevent migration of those formation fluids between all the different formations, for example, between the oil reservoir and the gas zones, or between the water and the gas zone, etc. So basically 3 objectives we try to achieve when we plug abandoned well. Now, to achieve those objectives, there are some regulatory requirements. And basically, the first is we talk about these requirements downhole. A downhole requirement is very much about permanent barriers. For example, in this picture on the right-hand side, plug 1, plug 2, plug 3, basically 3 barriers, permanent barriers for the permeable zones A, B, and C, shown in yellow. And in those permeable zones, it could contain oil and gas, or could be water, could be, other fluids, etc. So if the permeable zone, any of the permeable zone contains hydrocarbon, oil and gas, or overpressured water, the requirement is that we must have at least 2 permanent barriers to prevent the fluids from flowing through the wellbore to surface. For example, imagine the permeable zone at the bottom of the zone C, main reservoir contain oil and gas. We must have 3 permanent barriers, basically plug 1, 2, 3, and we have 3 barriers in this example. And also B, we have 2 barriers, plug 2 and 3. If the permeable zones contains normal pressure or low pressure permanent barriers. In the example, plug 3 for the permeable zone A, zone A. Now, when we talk about normal pressure, the low pressure water zone, what we mean is basically, even if there is no plug, no cement plug, or it's just a well filled with water, the water in the formation water will not be able to flow. So basically, plug 3 in this case, it's basically for insurance purposes. Other requirement, downhole requirement, is to prevent a cross flow between permeable zones. For example, in this example, plug 1 would prevent cross flow between B and C. Plug 2 would prevent a cross flow between A and B, etc. Now, in terms of requirement at surface, basically in an offshore environment, is basically we must cut and pull all the casing, basically remove all the casings, wellhead, etc., to below 10, 15 foot below the seabed. On the right-hand side, in green is a typical kind of a casing cutter tool we use for cutting the casing, cutting wellhead. So essentially, we're basically running this tool on the drill pipe. We're pumping water through the drill pipe. So the hydraulic pressure would open the casing cutter, and then we rotate the drill pipe to cut the casing. On the right-hand side in red is basically a casing cutting assembly. It's a subsea casing cutting assembly. In the subsea well, we must land the well on top of the wellhead, as shown in this example. And then along the bottom, it basically is a casing cutting tool, shows along near the bottom. And the picture at the bottom of the slide, we're showing an example of a casing and the wellhead being cut and pulled back to surface. In the middle could be very much a 9-5-inch casing and 13/3, and all sides could be 20-inch casing, etc. Now in the onshore also we have to cut the casing, all the casings to basically 3 foot below the surface. And also the well site clearings have to be agreed with the local authority for, native, depending on the native, the local condition, local environment, etc. We talk about the barriers for, the well plug abandonment, and talk about permanent barriers. Now, what do we mean when we talk about, say, permanent barriers? Basically, the barriers must provide a permanent seal. It's not basically last forever. Cement is the most commonly used material. usually could be probably certainly over 95, even 99% of the barriers are basically cement in a well plug abandonment. We can use other materials if we can prove, we can qualify those materials to have certain properties as listed here. For example, low permeability or non-permeable is not going to leak through the material basically. And the material will last forever. And the material is resistant to corrosion. Basically, that would eliminate typical steel, metal steel, for example. And the material must have sufficient mechanical strength to resist downhole pressure, temperature, and non-shrinking, to be able to bond with the casing and the formation, etc. As we said, typically the permanent barrier are cement plugs, and each barrier must have at least 30 meters in length of good cement. When we talk about good cement, basically what we mean is the cement, set cement must have a sufficient compressive strength, and which have to be modified by either applying weight on the casing using the drill bit, apply, for example, 10 to 15 tons weight. Or we can pressure test the cement plug. For cement behind the casing, we can use a cement bond log to verify the cement quality. Now, in some European countries, this requirement is 50 meters in good cement. In some cases, we can't get to good permanent barriers we talked about earlier, and we can use combination barrier to basically have 200 foot or 60 meters of a good cement to qualify as two barriers. Now, this is a quick example of wells before and after being abandoned. On the left-hand side is very much like a well we just drilled completed earlier. On the right-hand side, you can see the well having 3 cement plugs, 2 in red and blue and 1 in green. And of course, the top of the well, the wellhead and Christmas tree being removed. The other thing is when we come to plug abandoning a well, we must understand, know the well status of the well to be plug abandoned. Apart from the normal operations, a well basically could be in any status, especially the well to be plug abandoned, could be any of the remaining 3 status, be shut in, suspension, or already been plug abandoned, etc. Now, for those wells which might have been on production right up to the decommissioning or right before the decommissioning, those wells would be most likely in a shut-in condition. So when we say shut-in, basically what we mean is the well is closed at the Christmas tree, and also closed the downhole safety well, basically have 1 mechanical barrier. The downhole safety well is there at the Christmas tree. Downhole safety well is usually not considered as a mechanical barrier. Now, of course, we don't usually shut in wells for well plug abandonment. More often, the wells are shut in for routine maintenance, inspections, testing tree wells, etc., etc. Now, also for those wells which could be producing, up to several years or several months before decommissioning, several years before decommissioning, those wells would be most likely in a status of being suspended, basically suspension state. So instead of just shutting down close the Christmas tree, there will be also another downhole barrier we're going to talk about in the next slides. And again, we don't usually suspend wells for wells P&A, and more often for production wells, we suspend a production well because the well might have a downhole problem. So we need to do workover, to do stimulation, etc. For wells being drilled or worked over, we usually would suspend a well due to bad weather. For example, in Gulf of Mexico, the hurricane comes and you suspend a well to move the rig away. Also, could be geological reasons, etc., etc. Platform waiting for topside, you have to suspend the well for a few months, etc. And also the wells which there are some wells which may stop to have any economical value long before decommissioning. And for those wells, which would be most likely before decommissioning, would be most likely being abandoned or partially or completely being plug abandoned already. No, we just talk about the wells being suspended. This picture shows the suspended two different suspension wells being suspended. No, when the well is being suspended in comparison to being shut in, the wells need to have two mechanical barriers. For the production wells, usually apart from the Christmas tree wells being closed, most often is you will have a tubing plug in the tubing string, which provide a downhole barrier near the production packer. For wells being drilled or worked over, usually we would set the packer in the casing string below the seabed and below surface, and then you have the BOP as a surface barrier. And very important though, in comparison to the barrier used for the well P&A, in suspended wells would have barriers of temporary barriers, basically mechanical barriers. Basically, those barriers must be removed because they are not permanent barrier, must be removed before we do the well's plug abandonment. Typically, those barriers would be packers, bridge plugs, tubing plugs, etc. Now we're going to talk about some operational procedures, typical procedures to plug, abandon a well. In this first example is basically a well which has been still in a good condition when we come to the decommissioning. And basically there's no well integrity issues. And the well has already been shut in or been suspended, with the tubing plug, etc. When we do the well plug abandonment, the first step is to kill the well and set a cement plug number 1, as shown in this picture, to seal the reservoir. Of course, if the well is shut in, we must first open the tree wells to be able to pump in the fluids to kill the well. If the well is suspended, and then we have to run a wire line to pull the tubing plug from the tubing string before we pump and kill fluid to kill the well. And set the first plug as plug number 1 to seal the reservoir. Once the plug number 1 to seal the reservoir being set, and then we will run a perforating guns, a wireline gun to punch holes through the tubing to establish communication between the tubing and the annulus. And then we can pump in cement slurry through the tubing and into the annulus to set the cement plug number 2. And that would provide the second permanent barrier to the reservoir. And then we can cut the tubing string, cut the production casing to set the cement plug number 3, and then remove the wellhead, etc., to complete the well plug and abandonment. This is a relatively straightforward well P&A, as we can see that basically from a step 1 to number 4, basically you can pretty much do this on a platform, basically using the platform as an operational base without a rig, any workover or drilling rig. And then leaving the last 2 steps, probably perform the complete the well P&A before decommissioning. This second example is a well which have been having some well integrity issues, basically what we call the sustained casing pressure on the B annulus, basically the annulus, the cement micro annulus, micro cracks, basically. So the gas stones in the overburden formation leaking gas through the cement to surface. So we must stop the gas leak to provide a permanent seal to the gas zone. And the well also could be shut in, could be suspended. Now, so again, similarly, first step is to pumping cement to set the plug number 1 to seal the reservoir first. That's similar to the first example. But in this example, we must pull the tubing string to get access to the production casing. And then we can run wire line guns to punch holes through the production casing to get access to the cement and the formation outside. And then we can set the bridge plug, cemented retainer, and then we can squeeze the cement through the perforations into the cement outside and into the formation outside to set the seal, to establish the seal to the gas stones, to establish a permanent seal to the gas stones, which would provide the first barrier for the gas stone and the second barrier for the reservoir. And then we can cut and pull the production casing. In some cases, once you cut the casing, which could be 200 or 300 meters, you may not be able to pull the casing 200 or 300 meters length in one go. And you always try, but you may not be able to pull in one go because sometimes you got cement outside, some of the cement outside. If that's the case, we have to mill the casing, basically using a tool called the section mill, as they show in the middle of the picture in red, a section mill. And typically we mill the casing, say mill 10, 20 meters in length every day. As you can imagine, if 200 or 300 meters casing would take, just a milling casing could be 2 or 3 weeks. As you can imagine, this well plug and abandonment would take, much longer than the first one, and also will be certainly more expensive. Once the casing be removed, and then we set the cement plug number 3 and remove the wellhead, etc., to complete the well plug and abandonment. Now, this plug and abandonment well, I think in generally can be really not an easy decision to make because basically we are committing several $1 million, but without any return. And typically a well, which may be not economical today and $30, $40 oil price, but next year oil price might be high and the well might become economical again. And also, may not economical with the production currently, but with the new technologies of enhanced oil recovery, and then could become economical again. And also there are always constantly developing technologies for well P&As, and P&A operation become more and more efficient and more economical. So as you can imagine, always there's a tendency to delay the well's P&A to the last minute, basically. And also in terms of time and cost of our P&A, and hopefully through the discussion we have just talked about, it's very much dependent on the status of each well, dependent on what types of well. For example, in North Sea, Central North Sea, there are high temperature, high pressure wells, which would need more casing strains, which means more complexity, more issues, potential issues with our integrity issues, and therefore more complex, more challenging to abandon the well and more expensive. And also condition of each well depend on whether the well already have issues during the life of during its well's life. And also depend on whether you can perform an operation with a rig very much or without a rig. And which actually Alasdair, I'll hand over to Alasdair is going to talk about some new technologies being developed for wells P&A.
Thanks, Yuejin. So on the next final few slides, we'll consider and look at some of the technological innovations that are being applied to drive down P&A costs. After all, it's capital expenditure and there's no return. It's a necessary evil, so to say. And another thing to bear in mind is that the UK also has a target to reduce decommissioning costs by 35%. So operators must reduce the cost of well P&A. As we saw earlier, well P&A can contribute up to 50% of those overall decommissioning costs. And like Yuejin said, time and cost is mainly governed by the status of each well. We saw a question pop up earlier, or rather a statement, and indeed it's correct that some wells have been suspended for as long as 10 to 15 years as plug and abandonment has just been put off for all that time. The type of well, we saw earlier that subsea well costs are twice as much to decommission than platform wells. The condition of each well and whether rig or rigless operations are applied, as we'll see shortly. So onto this slide. Yes. So Yuejin has provided a really comprehensive overview of the procedures and touched on some of the conventional technologies, especially used for tubing and casing removal and barrier materials, which are highlighted on this slide. This is just a snippet from the Oil and Gas Authority webpage. Interest in plugging and abandonment technologies is really concentrated with the large and medium-sized operators who hold the greatest share of well stock to be abandoned. There are technology opportunities here to support in the kind of the organizational side ahead of operations, to make the process of well abandonment more cost effective and to introduce these alternative approaches. Again, operators have a growing interest in the benefits of this technology in this area and its contribution to the overall P&A costs in the UK. If we could just go on to the next slide, please, Yuejin. Thanks. Okay, so in this slide, we can see the main emerging technologies being developed. Interestingly, it's collaborative between the suppliers and the operators. And for example, so there's a prototype casing cement breaker, which has been developed by an Aberdeen-based oil and gas technology development company. I've got to be careful about disclosing any names here, but it's currently being developed in collaboration with Equinor, Total, and the Oil and Gas Technology Centre. The idea behind the tool is that it uses it's lowered through the casings and it uses pressure and rotation to manipulate the existing casing strings. And it breaks this bond between the well cement and the casing, as well as the structure of the cement behind the casing that Yuejin talked about earlier. And this reduces the forces needed to remove casings by around 50%. So we looked earlier at milling. Milling can be a very time-consuming process. So if we can find ways to reduce milling or get rid of it completely, then you're able to reduce time and therefore reduce costs. So the idea behind this cement breaker is that you successfully break the bond between the metalwork and the cement, and pull the casing out in one go. Yeah, milling is very slow and it's expensive, and it involves these tungsten and diamond bits which cut away at the steel, effectively turning it into small filings, and this breaker allows all of that to be taken out of the situation. Okay, so then another technology, another emerging technology methodology, and this is really interesting. I quite like this. Is the Bismuth alloy plug, again developed by a UK-based sealing solutions company in collaboration with Aker BP, which was first applied to the North Sea, Norwegian sector actually in the North Sea in 2018. So basically how this technology works, so it's aimed to replace your conventional cement plug. So what happens is you have this heater that's lowered down hole to melt these bismuth-based alloys. So the bismuth-based alloy is deployed downhole first in a solid form on an electric line, and then after you have the heater, which is lowered, it's activated, it melts the alloy, and basically it's so hot that it melts through the casing, it melts through the cement, it also melts the surrounding geological features, and creates this this big seal basically. And upon solidification of the alloy after the heating process, it expands like water. It expands like water to ice basically, and makes this gas-tight seal. It also has, when the bismuth in liquid form, it has some very unique qualities that make it ideal to sealing. In liquid state, it's got a viscosity similar to water, so it will penetrate all the small holes in the cement and the surrounding features, and it's got a specific gravity of 10, and due to its heavy density, it will flow into the well with gravity alone and doesn't require any surface pumping. And again, that saves time and resources needed to operate this kind of equipment. And lastly, it's non-corrosive, so it's not affected by H2S or CO2. Traditional well abandonment includes placing a surface cement plug through a section mill window. Eugene talked about the section milling earlier, or perforating, washing out the existing cement. And while cement at the moment is widely recognised as that standard abandonment material throughout the world, there are concerns that its ability to block gas in a well is lacking, because at the end of the day, cement is a porous material and it does shrink when it solidifies. So to reduce this potential, and I'll say potential environmental risk, and operators' long-term liability, this new material, this alloy-based bismuth is being promoted to ensure that the well is properly capped during the final abandonment operations. It also reduces significantly the amount of casing milling, which is normally required to allow the cement to bond to the plug. So you have to mill away the casing so that the cement plug can bond to the cement on the other side of the casing. And overall, yeah, really a nice example of how an innovative product is designed to cut costs and reduce operators' liability in the long term. But where I think we're really going to see operators reducing costs is the transition from rig to rigless P&A activity. So, yeah, thanks, Eugene. So what do we mean by rigless? Well, conventional plug and abandonment uses drilling rigs in order to carry out section milling, in order for a cement plug to be placed over the length between about 30 to 100 meters. To prevent leakage, that well casing, as we've discussed, is milled to allow the cement to bond to the rock, and done with conventional milling tools. Again, it's a labor-intensive, slow, and a very expensive, expensive process. To put into perspective, a modern DP3 drilling rig can cost, maybe not so much now, but certainly pre-pandemic, that rig could cost about $500,000 US daily. So some huge costs. And there are new technologies on the horizon. For example, one company has developed an alternative rigless coiled tubing technology, and that's based on plasma milling, which is a more efficient process. It also enables reductions in operational activities and equipment costs overall. These new technologies can be deployed directly to the platform, but perhaps more significantly, it can be deployed from a vessel rather than a rig. And that's really where we're making steps going forward. So in response to the introduction of these kind of technologies, there's a couple of companies out there who are forming exclusive entities to perform these vessel-based light well intervention services, one of which would be P&A. One company in particular has modified and dedicated 3 of their offshore vessels to well intervention services. This is one of their vessels on the right here, the Island Constructor. And really the message here is that rigless P&A operations have the potential to reduce P&A costs significantly, but it does go hand in hand with the continued development of the technology that supports it. But one real obstacle to the development of that technology is to get it over the line with the stakeholders. We predict it's going to be a lengthy project, lengthy time scale to get these technologies approved by the local governments, the regulators. So certainly a space to watch. And really, to summarize the last few slides, in respect to the technology, the cost of P&A activity to the operator is pure, and therefore we see the operators taking proactive steps to reduce those costs through collaborative innovation with their suppliers. These cost reductions are being achieved by emerging technologies. They're reducing the time to perform these activities. For example, the casing cement breaker, reducing the requirement for milling, perfing and wash, and which is very time consuming operations. And then lastly, the emergence of equipment that can be deployed from vessels. It's supporting the transition from rigs to vessels, which is really where we expect to see the biggest cost savings. You see in those daily rates. The downside, of course, is that not all of this technology, it's not always practical to use a vessel for P&A. And just conscious of time now, that brings our presentation to a conclusion. So I hope you guys have enjoyed it, and thank you for your time. And I think we'll now open up the floors to any questions.